Record. Hello, friends. This is Julia from the Macedon Public Library, Macedon, New York, and it is our Science Wednesday. And today we're going to hear about black holes and gravitational waves. So take it away, Brian, or come in, Brian.
Okay. Well, hello. Time for our weekly science thing. Annual. Hope it's not going to be annual, but I thought today I would talk about black holes and gravitational waves because they're an interesting part of astronomy and they're really new. So I will give you a basic background of the idea of what a black hole is. So if we look at a star like our sun, the reason the star shines, the reason our sun shines, is because gravity of all the weight of the sun is trying to collapse the sun on itself, trying to collapse under its own weight. And what happens is inside the center of the sun, the gas is compressed and heated so much that it actually fuses, like a nuclear bomb, or a nuclear generator. It fuses and creates energy, and that creates pressure that pushes back. So you have gravity trying to squeeze the sun, and the heat and pressure caused by fusion that pushes back. And that's also what causes the sun to shine. So eventually, the sun will run out of fuel, because all stars will, as they're fusing up hydrogen, they will all eventually run out of hydrogen to fuse. And so when that happens, depending on how big a star is, it will die in different ways. So our sun, for example, will try and fuse other elements as it's desperately trying to keep itself from collapsing. It'll swell up into a red giant, and then it will collapse into what's known as a white dwarf. So that is a star in which the pressure of electrons in the atoms keep it from collapsing. So basically, you can't collapse an atom on itself. So that's going to happen. Start planning, because it's in about 5 billion years. You're going to have to move. But if a star is larger than that, about 1.4, like 40% larger than the sun, then what happens is it goes through a similar stage, but when it reaches the atom stage, the white dwarf stage, the gravity is so much stronger that it actually does collapse the atoms on themselves. And so the electrons collapse, and what you get is just a ball of nuclei. You get a ball of neutrons, and that's called a neutron star. And that's where the neutrons push against each other and say, yeah, we're not going to collapse anymore. But if you have a really big star, then what happens when it collapses is it will collapse to the electrons, and the electrons collapse, and then it'll collapse to the neutrons, and the neutrons collapse. And there's nothing else to stop it from collapsing. So in that case, gravity wins. And so all of that matter of the star collapses and collapses and collapses to, as far as we can tell, basically a point. So it's the whole star that collapses down to something smaller than an atom. And in that case, what happens is the gravity near that collapsed star is so strong that not even light can escape it. That's what we call a black hole. So if you take all that matter and collapse it down to something that not even light can escape, then that's a black hole. Now, we know there are lots of them in the universe. We know that stars can collapse to form black holes. We also know that there's these really big black holes they call supermassive black holes that are in the centers of galaxies. And those are the ones that mostly we study, because they are millions or billions of stars collapsed all into a single black hole in the center of a galaxy. And our Milky Way galaxy has one. So about, I think 30,000 light years away is a 4 million solar mass black hole. And in the centers of most galaxies are these black holes. So We know that they're there for various reasons. Like we can tell that there's a black hole in our galaxy because we can see stars orbiting around this unseeable mass, because you can't see the black hole directly because it doesn't give off light. Light can't escape it. So you can only see the effects of it. So we see these stars spinning around this black hole, and we can say, oh, okay, that means there must be a really large mass there, and that's a black hole. Now, another way that we can see black holes is when they're actively consuming gas and dust around them. What they would say is an active black hole. The black hole in our galaxy isn't very active, it's passive. So we can only see it indirectly. But some galaxies are actually consuming gas and dust around them. And when they do that, the gas and dust heats up so much that you get these powerful radio waves or powerful X-rays, and we can see that light. So we can't see the black hole directly, but we can see all of the hot gas and dust around the black hole. And that's mostly how we see black holes. So we've been doing that for a while. I mean, since I was in graduate school, we've been able to see these kinds of supermassive black holes and study them and things like that. But if you want to be contrary, you could say, well, it may be a really dense mass, but I don't think it's a black hole, because all sorts of weird things happen if it's a black hole. You would enter a black hole and could never get out. Like it's impossible for anything to get out. Well, that's really weird. You kind of have like a one-way path, things like that. So some people have said, well, it may be very dense, but it's not a black hole. You're not seeing a black hole because what you're seeing is all this hot gas and dust. And it's true that if the object were very, very, very dense, but not a black hole, then yeah, it would look very similar. You would see the hot gas and dust around it. You would see stars orbiting around the center of whatever it was in our galaxy, but it wouldn't be a black hole. So how do we know that they really are black holes? And the answer was two ways. One was there was nothing we knew of in all of physics that could stand up to the gravity of something that massive and that dense. So the idea that something would collapse and then not collapse into a black hole, there would have to be something preventing it from collapsing into a black hole. Well, it couldn't be atoms, it couldn't be nuclei, it couldn't be anything in particle physics. There was nothing that we knew that could prevent things from collapsing, which is why most astronomers would say it's got to be a black hole. But in the past several years, we've been able to do things that we'd never been able to do before. And one of the big ones is we can now look at not just the light coming from near a black hole, we can actually look at what are called the gravitational waves of black holes. So if you look at all of astronomy, ever since before Galileo, when we look up in the night sky, what we see is light. And so when astronomers study the universe, the only thing they can study is light. So visible light, radio waves are light, X-rays are light, infrared and ultraviolet, that's all light. And the thing about light is that it can be absorbed by gas and dust, and it can be emitted by gas and dust. So it's kind of like if you have a blanket with holes in front of you, you're trying to see through it. Light gets absorbed and light gets emitted, and so it's hard to see some of the things. And a black hole doesn't give off light, so we can't see it. But one of the things that Einstein did in relativity was show that gravity is something very weird. Gravity we think of as a force that pulls us to the Earth, or that holds the planets in orbit around the sun. And that is one way to look at it. But what Einstein showed was that if you look at gravity really closely, it actually has some weird properties. And one of them is gravity, the mass of an object, causes space to twist shape. It changes shape. So you think of space as just being go in one direction, go in another direction. It's just length, width, and breadth. It's empty. It doesn't have anything to it. It's just where you happen to go. And what Einstein showed was no, actually, space itself is affected by the mass of an object. Gravity can be seen as a curvature of space, a shifting of time. There's all sort of weird things that gravity does. And this was, when he proposed this, it sounds like he's out of his mind, but it actually works. So one of the ways that we found out that it worked was that light, since light isn't made out of stuff, it shouldn't be affected by gravity. And we found that light was actually attracted to masses. So you could have a star, and a beam of light would go near the star, and then it would change direction slightly, exactly like Einstein predicted. More down to earth, if you ever use a GPS in your phone, it has to take into account the curvature of space, the shifting of time by gravity in order to be accurate. So if you program, basically GPS works by having these satellites that are orbiting the Earth, and your cell phone listens for the signals that these satellites are sending. And then it says, well, if there's a satellite there, or there's a satellite over here, and I'm here, then that means I can do some complicated math and go, oh, I'm at this spot on the Earth. And that's what it does. It's kind of like if you were to walk around your neighborhood and go, oh, well, the red house is at the corner, and I see the white barn there, so I must be on Main Street. Because you know what you can see from a different location. GPS does the same thing, but it picks up radio signals from these satellites that are orbiting. It says, oh, I can hear this satellite and this satellite, so I must be here on the Earth. In order to do it right, you have to account for the fact that the Earth, the mass of the Earth, is shifting the space around it. And so you can't just have a simple clock in your satellite. You have to have a clock in your satellite that accounts for that shift. And if you don't account for that shift, your GPS doesn't work. So when I was teaching things like Einstein's theory of gravity, I would tell my students that if you use your phone to figure out where the latest Starbucks is, you're using a $200 device to connect to a $3 billion system of satellites to test Einstein's theory of relativity. And if you can find coffee, then Einstein was right. And so what happens is, because masses shift space around them, what happens if you have a mass that moves? Well, now that mass that has shifted space around it is now moving through space, and that's like moving something through water. If you have a boat sitting on a lake, and then you move the boat, well, all of a sudden you've got these ripples of water that are coming out from where the boat moved. Well, the same things happen with masses in space. As the Earth moves, it causes these ripples in space to go out, these waves of space, which we call gravitational waves, because the shifting of the Earth is causing these ripples. Now, these are really, really, really small ripples. You're not going to feel them. You can't really see where they are. If you could feel them, they would feel like you're being kind of squeezed and pulled for a little bit as the gravitational wave goes past you. You can't feel them. However, when you have, say, one large black hole that's orbiting another large black hole, so you have two black holes that are orbiting each other. If those two black holes are orbiting each other, they're moving through space, and they're creating gravitational waves. And so what happens is you have these black holes, and they orbit and orbit and orbit, and eventually they get closer and closer and closer together until they collide. When they collide, they merge together into a single black hole. And these are called black hole mergers. because you have two black holes that orbit each other, and then they create a single black hole. So, and that sound I made is similar to actually what we detect. So we actually have now, and we've had it for a couple of years now, these telescopes, but they don't detect light. They detect this oscillation as the gravitational waves go by. So they're called, one of them is called LIGO, another one is called Virgo, but basically they're a set of mirrors that are placed in just the right way, and you shine laser light between these mirrors. And as the gravitational waves pass by Earth, these mirrors just go as the gravitational wave goes by, because the gravitational wave is squeezing them and pulling them. And so they go, and you can see by bouncing the laser, you can see whether they got closer or farther apart. And so as the gravitational wave goes by, you look for that ripple, and then if you put it on a computer screen, it looks like this little oscillation thing that goes up and then dies off. And if you make it into a sound file, it goes whoop, and that's it. Because what's happening is these two masses are orbiting faster and faster and faster, and then they merge. And that ripple stops because they've merged together into a single black hole. And so you can actually watch, if you have your gravitational wave telescope, you can see these things, the gravitational waves showing that they've gone faster and faster and faster and faster and then stopped. And so we can see now black holes that have merged. When they merge, they create these strong gravitational waves, and then they drop off as soon as the two black holes have merged. Now we've, over the past few years, detected a lot of these mergers. And the thing is that if you do this and you look at the data the right way, you can say, oh, well, we know based on how it merged that black hole A had a mass of, say, 3 suns, and black hole B had a mass of 20 suns, or things like that. And so you can figure out what the masses were and how they merged. Now, what's interesting is that one of the things you can show is if they were not black holes, then they would have a different pattern. So for example, if they were 2 neutron stars, those things that are not quite big enough to be black holes, they would have a different pattern. And you would see that. And so by looking at black hole mergers, we know these things are black holes. We know that that's what they have to be. One of the things that this has really changed in astronomy is that for the first time, we can now look at things not with light. So basically, all of astronomy, from the dawn of history up until 2017, was all entirely done only by looking at light. And once we had a gravitational wave telescope, we now can look at things not with light waves, but with gravity waves. And those don't get absorbed by gas and dust. They just pass right through it. So for gravitational waves, all the gas and dust and everything that we see in the universe are invisible. They're transparent. So the gravity waves just pass right through it. So what we can do is we can see things that we wouldn't be able to see otherwise. We can see things like black holes now. We can do experiments like finding out how far away something is and not have to worry about, well, it's because there's dust in the way or anything. Like one of the ways that we see how far away something is we say, well, we know how bright it is. And if it looks this much dimmer, it must be that much farther away. It's kind of like if you had a flashlight and you knew how bright the flashlight were, and then you saw one that was fairly bright and one that was really dim, you'd say, well, that dim flashlight has to be farther away, because the more distant it is, the dimmer it will look because it's so much farther away. Well, we can do that with starlight and say, well, this star must be farther than this star. But that assumes that there isn't any gas and dust in the way. But with gravitational waves, gas and dust doesn't matter. So we can actually figure out how far away things are. So there's like this whole new thing of seeing the universe that we've only just been able to do. Any questions? Or are you just like waiting for it to all kind of sink in?
Yeah. Wow.
I mean, one of the really interesting things is the fact that all of history has been light. Like we've always been limited by light because that's the only thing we could see. And now we can see light waves and gravitational waves. So we have two ways to look at the universe. And one of the cool things that's starting to happen now is to combine them. So it's something that they call multi-messenger astronomy. Multi-messenger meaning light is one messenger, gravity is another messenger. And so we can start looking at how things work. So one of the cool things related to radio astronomy, for example, which is what I'm connected to, is we're looking for what happens when a black hole and a neutron star merge. So when that happens, you can find the gravitational waves, so you can see the gravitational waves. But also what happens is as the black hole and the neutron star collide, the neutron star gets ripped apart. And as it gets ripped apart, it gives off this powerful burst of radio waves and other light too, because the black hole is basically ripping apart this neutron star. So if you can find that neutron star black hole merger, then you can look in radio light and you already know what the two masses of the objects were, you know how far away they were, you know what they were doing. And then when you look in radio light, you can say, oh, that means that the inside of the neutron star must be this. Because you can see what was happening when it was being ripped apart. So basically you can have a black hole rip apart a neutron star and then say, oh, that's what they're made of. Which we couldn't do before, because if we saw one of those and we only saw it in light, we'd go, well, that's a burst of radio light, but what's going on? Because I know what the light is, but I don't know what's causing the light. And I don't know when it is a solid neutron star and when it's a ripped apart neutron star. And so with gravitational waves, by combining the two, you can do both. You can find out more about neutron stars.
How long does it take for the black hole to rip apart a star, though? How long? What time period?
So what happens is when you have the neutron star and the black hole orbiting each other, when they're fairly far apart, it can take thousands of years for them to get close enough. But when they get close enough that they're going to merge, it happens really quick. So when I made that sound where it goes, that's actually kind of slowed down by a factor of 1,000. So in real life, if you do it in real time, then what it is, well, they're orbiting really closely, and that's it. Pop. It's a tiny fraction of a second.
Wow.
And that's because gravity is so strong. These things are moving at almost the speed of light.
Hmm.
And the speed of light can go from the Earth to the moon in 1 second.
Wow.
Or it can travel, what is it? It can go from New York to Los Angeles and back, I think, 20 times in 1 second? Something like that. So it's like, it's extraordinarily fast.
Yeah.
Hmm.
Amazing.
It's amazing we could record that.
Yes, it's so here's one of the things that's really freaky about how these detectors work. Not only do the signals have to be recorded really quickly, but you're actually, when I say these mirrors are oscillating back and forth, they're not oscillating very much. They are oscillating by such a tiny amount that the surface, the distance between the two mirrors shifts by less than the width of a nucleus of an atom.
Whoa.
So they are basically, you have to build these mirrors so they are as stationary as you could possibly make them. The entire thing is isolated, it's set in a vacuum, and then they're suspended by these crystal wires so that everything will be isolated and they will not move from anything outside. The only thing that can move them is gravitational waves. And
Well,
even when
wouldn't
you do everything possible to prevent them from moving, it is still moving slightly because of the Earth just
Yeah, that's what
rumbling, like little tiny vibrations. In fact, one of the things that's happened now is because of the quarantine, the data is getting better because people are staying home more. So the Earth, the little vibrations of the Earth are actually died down because nobody's all out on the highways, and because we all go out and walk and move and cars and flies, all of that makes the Earth just kind of jiggle a little bit by very, very tiny amounts, but these gravitational wave detectors can measure that. And so it's actually gotten a little bit quieter, so it's easier for them to do the data. So it's actually this extraordinarily sensitive thing to measure the merging of two black holes, or a black hole and neutron star, 1 million light years away. So we're actually measuring mergers that occurred before there was even human civilization.
Oh, wow.
And then we built it, and now we're seeing them.
Or do you look out?
Wow.
It's- yeah, I mean, there's a reason why it got a Nobel Prize.
Yeah.
Yeah.
Mind-boggling.
Which means in 50 years we'll have undergraduates do it and say you have to do this to pass.
Oh, gee.
It tends to be how it goes. That
Amazing.
prizes, experiments that won Nobel Prizes 100 years ago, we make students do it and say, oh, you
Just
have to
part
do
of the
that.
class, do it.
That's right. That's right. You just have to do that now. You thought things were easy. No, they're harder. But
Makes
But
me
yeah,
glad.
it's a very new field. So,
Very interesting.
Yeah. Great.
Yeah.
Very interesting.
good.
Again,
So, do you have any questions or anything, or do you have any questions?
too much.
You've heard this all before. Yeah. She gets tired of this.
No, but it's your dissertation.
Yeah.
As long as I've known you.
Yeah. She's heard all the stuff about black holes because that was what my dissertation was on.
Oh.
And it went from so what did you learn today? And I would go on and on and on like this. And then it very quickly became, did you make progress? Yes. Good. I don't need to hear it. I'm glad you made progress.
Moving on. Oh, very good. I think I'll watch this. I think I'll watch this on the video because it's too much for me to take in at one
It's a
time.
ton of information. Yeah.
So I'm going to watch it again, and that will help.
Okay. Okay. Well, if you watch it again and you still have questions, by all means ask.
Well, you
I'll
pretty
be here
much
next
answered
week. So
You pretty much answered my question. I was going to ask if those mirrors, there must be some movement to them from the Earth rotation and wobble.
there is. It's
You answered
actually
that.
the worst part about it is just random, like, distant noise. So if there's a minor earthquake in India, it actually causes the detectors in Alabama to jiggle a little bit. So this is part of the reason why we don't just have one gravitational wave detector. We've got one in Alabama and one in Washington, and then there's another one in Italy.
Oh.
And the reason is because if all of those three detectors, if there's a little tremor or literally somebody sets off a stick of dynamite in India, those sound waves, those oscillations go through the Earth, but they travel at the speed of sound in the Earth. So the detectors would go, oh, I saw something. Then the sound wave would keep going, and then, oh, it hit Alabama. Oh, it hit Washington. But it travels at the speed of sound.
Yeah.
Gravitational waves travel at the speed of light. So what you would get is bang, bang, bang. And then, oh, that traveled at the speed of light. That's a gravitational wave. And that's really the only way that we know. So that we can say, oh, that flagged all 3 detectors separated by a distance of the speed of light. So that means it's a gravitational wave. You see a little spike, and then a spike, and then a spike. And that tells you it's a gravitational wave. If you just had 1 detector, you'd go, I'm seeing noise here. I got nothing, I got no data to say whether this is a gravitational wave or not, because I don't know where it's coming from. All I'm getting is, well, there's oscillation. Well, that's nice. And even then, even with the 3 detectors, you still have to run through all of this data analysis to filter out all the noise and pull out that one signal that hits all 3 of them. And it's only when you get
Where is
to
it?
you say, well, that is a confirmed event.
Where is it in Alabama?
It's near Huntsville, I think.
That's where our son lives.
Yeah. So yeah, there's 1 in Alabama and 1 in Washington, because they're widely separated in the United States, and they also get 2 separate universities and 2 separate, Senate districts and all of that. We love to do that. But now we have 1 in India, and there's I think it's either South Korea or Japan, I think, is building 1. And then we'll get even more precise. So the more observatories we get, the more precisely we can get. Because one of the things we can't do yet is say exactly where it comes from unless we see a radio flash as well. So basically we're like 2 moons wide in terms of where it might be. So it's somewhere in this area of the sky. Well, if we get another detector, then we can narrow that down. If we get another one, then we can narrow it down. So that pretty soon we can say it's there. But we need like 5 or 6 detectors to do that. So we're getting there. Other people are building them now, but it's going to take time. So,
Good.
we are. It's only a few years old, and in 100 years it'll be a long established science. But right now it's brand new.
I like hearing about the cutting edge science.
This is about as cutting edge as you're going to get in terms of astronomy. That's a huge thing in astronomy for being able to do that.
Wonderful.
And it's a big jump. So yeah.
Okay.
Yep.
Okay.
Okay,
Thank you
well,
once again.
you're very welcome. And like I said, if you have questions, ask. And if you have other ideas, email. What's the email address? Oh, just
No,
email
that's
Stacy,
right.
Julia
That's
says, if you have questions or ideas for topics. Otherwise, I'll come up with something.
Okay.
Okay.
Wonderful.
Okay.
Good job.
Looking forward to it.
Okay. Thank you very
Thank
much
you.
for attending. And I guess I will see you next week.
You
You
will.
bet.
Bye.
Bye. Did I end the meeting? I think I did.